Assalamu alaikum, dear students. Well, this time we are taking one more this lecture. It will be now lecture number 10. Lecture number 10 on solution of ordinary differential equations, and up to lecture number 9 we did the differential equations of first order and first degree, how to reduce the differential equation into homogeneous form, reducible to homogeneous form, and solution of homogeneous differential equations, and we discussed that in detail, and we have also discussed with you some applications on that. Well, now we come to these linear differential equations. Actually, these are the linear differential equations of first order and first degree. You see how we introduce this. This is a very important concept. We define this in this way. This is the introduction of this. Introduction. We define a differential equation having dependent variable, say we take it y, and it is derivative, it is dy by dx, the dependent variable y, and it is derivative dy by dx when they occur in first or degree only. We define a differential equation which have dependent variable y, and it is derivative dy by dx in first degree, and are not multiplied together. These are not multiplied together, means in this case you don't have y into dy by dx. If it has, we are in that case trying to just reduce it into linear differential form. That will come to in the this what is known as Bernoulli's equation. But here we say, when we talk of the linear differential equation of first order and first degree, their dy by dx is of degree 1 and degree of y is also 1, and they are not multiplied together. We write here the standard form of a linear differential equation, standard form of linear differential equation of order first. There we said degree is 1, dy by dx is of first degree. Now we say it is of order first is what? Is dy by dx plus py is equal to q. This is the standard form that we take this linear differential equation of first order and first degree. What is the peculiar property that you observe here? Dy by dx of first degree, it is degree is 1, and the dependent variable y is occurring here in the first degree. The power of y is also 1. This is how to recognize. But one more thing is very important here that I will mention here. It is very important, where p and q are functions of x alone. These are functions of x alone or can be constants. These are functions of x alone or can be constants. What we mean by this? You don't find any y in this p, you don't find any y in this q. It is either constant or function of x. What is then y? Y occurs throughout in the linear form, and dy by dx is in the first degree and first order. This we define as the linear differential equation of first degree and first order. Degree is also 1, order is also 1. Let us now discuss the method of solution. Is very important method of solution. It involves something in the method of solution known as the integrating factor, but that we derive later on. Here we will introduce that. This is actually the 10th lecture we are delivering on this. Let us have the it is method of solution of linear differential equation that we are taking at this time. In future we may have some other linear differential equations of the nth order, so on and so forth, but here we say it is a standard form of the linear differential equation of first order and first degree. Well, I will again consider here our this linear differential equation. Consider the linear differential equation which is our dy by dx plus py is equal to q. This is our linear differential equation where we have p and q, where p and q are functions of x alone or can be constants. They don't involve here y in p and q, and y throughout occurs in the first degree. Well, how to solve it? We introduce or here I will say we define. Later on you will come to know where from it we get it. We introduce or define a factor. It is e raised to power integral of p dx. P is some function of x and y. It is e raised for integral of p dx. Very important factor. You may put a question here where from we get it. This is actually in advanced studies of differential equations. When we talk of this integrating factor, we have there the different methods for finding out the integrating factor. Now, what is the purpose of integrating factor? What we get from integrating factor? Integrating factor is a multiplying factor. When we multiply a given differential equation by the left side, and this factor makes the differential equation as exact differential of some function. It has a peculiar property, this multiplying factor. It reduces the differential equation into the derivative of exact differential of some function of x, some function of x and y. This integrating factor we get in future studies. The method how to find out there are different methods. We may discuss some methods in future when we take exact differential equations. There we have the exact differential equations integrating factors which help us to reduce the differential equation into exact form. Here we introduce, but what is the peculiar property here of this factor, multiplying factor? This factor has a peculiar property. I will write here it. By multiplying equation number 1, that equation, by this factor e raised for integral of p dx, the left hand side of equation number 1, the left hand side of equation number 1 is the exact differential exact differential of some function. Here also, when you will see, when we multiply both sides by this factor, our left hand side of this first is exact differential of some function. That is, left hand side of first is exact differential of some function of this. You see, it has a peculiar property. Now let us multiply this equation number 1 by this factor. You have to remember this factor, right? This is a method of solution. You have to remember this, how we find out this, how we write the solution by this, and where from we get this factor. You will get the answer to that question in future studies of advanced this differential equations, when we find out their integrating factor. Okay. Now how we do it here, it is very interesting. You see what is the function and working rule of this factor. Now we multiply this multiplying both sides to first by this factor e raised power integral of p dx. When we multiply both sides, what we get? It is e raised power integral of p dx. This is dy by dx plus py. This is same p. It is py, which is here. Function of x, I'm sorry, this is function of particular function. It is this p. P is function of x, the same p. Py is equal to e raised power integral of p dx into q. You see what is this now? This you can write e raised power integral of p dx into dy by dx plus this p e raised power integral of p dx y is e raised power integral of p dx q. Now you look here, where I get this p, it is the coefficient of y. When the given differential equation is expressed in standard form of the linear differential equation in this form, where y is existing at only one place in the coefficient of p, then we define a factor. It is e raised power integral of this p dx. P is a function of x. Then we multiply both sides by this. There is a particular property. You see how this is reduced to this. I write this. You see what happens to this. I will write this left hand side. This left hand side is now what? Your left hand side becomes by this. It is d by dx of y times e raised power integral of p dx is equal to e raised power integral of p dx into q. Now you may ask a question here, how this becomes this. It is where you see how we go. I will explain here. First I will let you know. You know, suppose you have the derivative of e raised to power mx with respect to x. How you go? You write exponential function as it is, then differentiation of power. What is power? Mx with respect to x. We go like that. I will differentiate this. You know this thing. You see how we go. What is my differentiation with respect to x of y e raised power integral of p dx? You see what is this? I am differentiating this. I am actually explaining this to you, how this becomes this thing. Okay, let me see. Apply product rule. Derivative of this, it is dy by dx. Then second function as it is, e raised power integral of p dx, then plus y as it is, derivative of e raised power integral of p dx with respect to x. Do you follow? Derivative of this function first, then second as it is, then first as derivative of second. Now here I am just explaining you how this is. It is e raised power integral of p dx dy by dx plus y times, what is the derivative of this? Yes, it is an exponential function, e raised power mx. What is exponential? Exponential function as it is, e raised power integral of p dx. Okay, exponential function as it is, then differentiation of power with respect to x. How you go? Then you write differentiation of power is integral of p dx with respect to x. Do you follow? Here differentiation of this, it is this, then y, differentiation of this, I am writing derivative of this here, it is a derivative of exponential function, then exponential function as it is this, differentiation of power, it is derivative of integral of p dx. Then you have one more thing, what is that? Log of base, log of e to the base e, you know it is 1. Now you see what is derivative of this. How you find out derivative of this? It is derivative of integral of p dx. It is integral. It is an integral. Integral and derivative are reciprocal of each other. This will give you only p. What does this gives you? It is e raised power integral of p dx dy by dx. It is plus y. It is y e raised power integral of p dx into p. That means you get this. It is this setup. You see, it is this e raised power integral of p dx dy by dx plus p e raised power integral of p dx into p. You have got this thing. You just see, look at this setup and at this setup. How have we got this thing? When I differentiated y e raised power integral of p dx. So I can say this is nothing. It is the derivative of y e raised power integral of p dx, because when I differentiate this here with respect to x, I get this thing. It is this. Clear? So this is the peculiar property of this factor, and how we get it? It is in advanced studies of differential equations when we deal with in finding the integrating factor. I will put it in the note later on. So you see what is the utility of this factor. So it has reduced it to this way. Now what I do is I integrate on both sides. Now integrating this on both sides, integrating both sides with respect to x. Now it is differential, d by dx. When we integrate it, reciprocal is it, you get only y e raised power integral of p dx is equal to, it is integral of e raised power integral of p dx into q dx with respect to x plus c. This is the solution of this differential equation. Now we have seen the solution depends upon the main thing which is known as this integrating factor e raised power integral of p dx. When the given differential equation takes the standard form of the linear differential equation, where y is linear, where dy by dx, p and q are either constants or functions of x, then we can directly write the solution is this. This is the particular property of this integrating factor. This is solution. Solution is okay. Now I will just write the note on the definition, then I will go to application part, then I will write some applications on this. Let us have some, it is just, I will name it remark on the definition. Remark, sometimes we write it observation on definition. A remark or observation on definition. We go like this. In solution of the differential equation, which is dy by dx plus py is equal to q. The multiplying factor, e raised power integral of p dx is worked out in advanced differential equations where we find integrating factors, where we find out integrating factors, and in future studies in differential equations we shall come across this integrating factor, this integrating factor working rule. What is the working rule for this integrating factor? Here we don't need, we simply defined this E raised for integral of p dx, but in advanced studies this is worked out in advanced differential equations where we define integrating factor. There we find out this E raised for integral of p dx. By this method, in short form, what we do is now, in short form, we write integrating factor as e raised power integral of p dx in this equation. And what is the solution? The solution of dy by dx plus py is equal to q. How we remember to write down the solution of this differential equation? Well, we write the solution now. The solution of this is, in short form, it is y into integrating factor that you find is equal to integral of, here integrating factor, your q dx plus c. This is the short form to remember the solution, where you denote this integrating factor e raised power p dx. Further, if x is our dependent variable now and y is independent variable, in that in dy by dx plus py is equal to q, our y was dependent variable, x was independent. Now if x is dependent and y is independent variable, what is the form of this linear differential equation? The linear differential equation of first degree and first order in this case will be, it is dx by dy plus px is equal to q. There previous was dy by dx plus py is equal to q. Now what is this now? Dx by dy plus px is equal to q. What is here p and q? Where p and q will be functions of y alone, or it can be constants. And in this case, what is integrating factor? What is integrating factor in this case? So in this case you will write integrating factor. Integrating factor in this case will be, remember this, it is now e raised to power integral of p dy. There it was integral of p dx, it is p dy. Your p here will be constant or function of y. Now how you will write down the solution? What is solution? The solution will be, well, the solution of this type of equation is, the solution in this case will be, it is x into integrating factor is equal to integral of q into integrating factor with respect to y will be now plus some arbitrarily constant. It is the solution of this type of differential equation where p and q are functions of y. X is occurring here linear form. X is occurring linearly, dx by dy in the first degree. So solution will be x into integrating factor, integral of q into what is integrated factor, e raised power integral of p dy. This is how we solve this. Solution is very simple. Let me have some applications. We will now deal with some applications. Well, dear students, I have written here some applications. These are some applications how we solve these differential equations by previous method. You see solution. I will write this differential equation where I have to solve 1 plus x square dy by dx plus 2xy is equal to 4x square. Just have a look to this differential equation. I am observing that dy by dx is in the first degree. I am also observing here that y exists in the linear form. There is no y square. So there are maximum chances to reducing this differential equation in the form of dy by dx plus py is equal to q, because y is here linear. So I have to get rid of this. If I have to write this in this form, dy by dx plus py is equal to q, then write the integrating factor. I have to put it in this form. If I can put it in this form, then it is very easily I can write down the integrating factor. This should be p and q function of x alone. Now for that I will divide this. Divide both sides by what? 1 plus x square. When you divide by 1 plus x square, it is dy by dx. Yes, plus 2xy by 1 plus x square is equal to 4x square by 1 plus x square. Oh yes, it has now taken the standard form. It is differential equation of this form, dy by dx plus it is 2x by 1 plus x square y is equal to 4x square by 1 plus x square. This is my differential equation now, linear differential equation of standard form. It is dy by dx. This is your py. This is q. Q should be a function of x or constant. P should be a function of x or constant. Y should be linear. It is. So it is of this form. Dy by dx plus py is equal to q. What is my integrating factor? First step is to put the differential equation in the standard form, then write. If you don't have it in the standard form, then your integrating factor e raised power integral p dx will not be perfect. If you want e raised power integral p dx in this form to be perfect, put it in this form or in the form of dx by dy plus px is equal to q, where p and q are function of y. Now here my p is 2x. I need only here p and q. My p is 2x by 1 plus x square. I can write also my q is what? 4x square by 1 plus x square. Now I have to find out in the first setup, I have to find out my integrating factor. Integrating factor is e raised power integral of p dx. That is your e raised to power integral of 2x by 1 plus x square dx. It is equal to, now look, what is this? E raised to power integral of 2x by 1 plus x square. It is f dash x by fx. Derivative of 1 plus x square is 2x. Directly you get it. 1 plus x square derivative is 2x. It is f dash by fx. It is log of fx. It is log of denominator, log of 1 plus x square. Yes. So I write just here. You see, my integrating factor is now, my integrating factor comes out to be, it is e raised to power log of 1 plus x square. Actually it is to the base e. Do you follow? It is e raised power this, it is f dash by fx. When it is derivative integral is f dash by x, it is log of the denominator, it is 1 plus x square. Now here you have a formula, you know, if you have e raised to power log of m to the base e, it is nothing, it is m. It is e raised power log of this to the base, it is your 1 plus x square. 1 plus x square, it is your integrating factor. Okay, so what is solution? How do you write down solution? I need only q here. Well, my solution is now, so general solution is, I will write it, solution is y into integrating factor is integral of q into integrating factor with respect to x plus c. This is a shortcut method for writing down the solution. It is y, what is your integrating factor? It is 1 plus x square is equal to integral of, what is your q? Q is your 4x square by 1 plus x square. This is your q. What is your integrating factor? It is 1 plus x square. This is your c, arbitrarily constant. Dx is here. This and this goes. It is 1 plus x square into y is 4 out integral of x square dx plus c. So what is the solution? Well, the solution of this differential equation will be 1 plus x square into y is 4, it is x cube by 3, I will write 4 by 3 x cube plus c. This is the solution of this differential equation. This differential equation, when we could put it in the form of dy by dx plus py is equal to q. This is how we proceed. Let me take one more example I have given here. Well, I will solve one more. Solve this second solution to this different. It is dy by dx is equal to 1 minus x plus 1 minus y. Here I am observing that y is linear. Even x is also linear, but to write it in the form of dx by dy will make the things complicated, because this will also get reciprocal. So I will write it in the form of dy by dx plus py form. This is your dy by dx is equal to, it is 1 minus x plus 1, okay. Dy by dx, take y on left side, plus p is equal to 1 minus x plus 1. Well, it is dy by dx plus p, sorry, p not, it is y. It is y, this is y, is 2 minus x. This is the linear differential equation of the form dy by dx plus py is equal to q. What is your p here? Coefficient of y1. What is your q? It is 2 minus x. So what is integrating factor? It is e raised power integral of p dx. E raised power integral of p dx. What is this? You will write it. It is e raised to power integral of your p dx. Your p is 1. It is 1 with respect to x. So your integrating factor is e raised to power x. This is your integrating factor. So what is the solution? How you go to solve this? What is the solution of this differential equation? What is solution? You write the solution of this differential equation as it is y, your integrating factor, then integral, your q, your integrating factor found with respect to x is there, plus c is constant of integration. This is your y. What is your integrating factor? E raised to power x is equal to, what is your q? It was q is 2 minus x. It is e raised power x dx plus c. Okay. Now how I integrate this? It is the linear function and exponential. I take here, take u is equal to 2 minus x, v is equal to e raised power x, then integrate by parts. Integrate by parts. You can integrate by parts. I mean here it is y e raised power x. Do you know how we integrate by parts? It is u as it is, integral of v with respect to x, then minus whole integral derivative of u with respect to x, integral of v with respect to x. What you get is to be integrated with respect to x, plus c is constant of integration. Well, it is your y e raised power x is equal to, what is your u now? It is 2 minus x. What is integral of e raised? It is e raised power x minus whole integral. What is derivative of this with respect? It is minus 1. Then integral of e raised power x is again e raised power x dx plus c. You see what you get? It is y e raised power x is equal to 2 minus x e raised power x. This is plus integral of e raised power x plus c. You can say this is the solution in complete form. But if you write the solution in just simplified form, you can go this way also. It is y e raised power x. You can take e raised power x here. It is 2 minus x plus then 1 plus c by e raised power x. You can go this way also. This means solution is e raised power x, you can get cancelled. It is y is equal to, it is your 2 plus 1 is 3. It is 3 e raised power x goes 3 minus x plus c e raised power minus x. This is the solution of this differential equation. Do you follow me? Okay, dear students, I will stop here because we have to offer the namaz at this time. I will show this problem. I will also deal in another lecture. It may be this video lecture 12, and some more applications we will do there, and gradually we will reach then Bernoulli's differential equation. I hope you are doing properly at your places during this lockdown period. And this period, you have the books at your disposal, and you will do maximum problems from your reference book, from your textbook. If there is any other problem, you can put the problem in my comment box or in through my WhatsApp. Thank you very much. I wish you all the best and see you next. Thank you very much.